Let's get started. We're having some trouble with our computer again. But first, there have been questions about the midterm exam coming up next week. So I believe this is the kind of information you may want. First of all, of course, the topics with chapters 20 to 25, just the material on electricity, nothing on magnetism. That will be the next one. Okay, but that's inclusive, includes chapter 25. Now there will be a GSI review session on Saturday from 12 to 2, noon to 2, in 155 Dwinell. You're welcome to attend. That's our section. The two sections, pretty similar, but not exactly. So he's going to try to focus more on our topics and approach, I hope. The exam itself is on a week from this Wednesday, that is the 4th of March, 7 to 9, in 2050 Valley Life Science building. Yes, sir. Doesn't hurt. If you got time, do it. Yeah, sure, you'll always learn something. Yeah, I believe so. I believe Dr. Lebau is doing similar to 20 to 25. If he goes on to magnetism, no harm either. But it'll certainly emphasize the first 6 chapters. And of course, I sent out a memo about other tutoring and review sessions that are offered by various people. Have any of you attended those so far? Is it good? You tried? No, nobody tried it even. I guess you know everything, so why bother? No. It's just good to hear it from different points of view. Of course, you want to hear it accurately, and I can't vouch for what other people say. I mean, they're offering tutoring, but I personally have not met the people who are doing it, so I don't know how good it is. But if it's wrong, you want to be able to go there and say, hey, that doesn't sound right, then, that starts a discussion, and maybe you can dredge out the truth. So everything is good. Today I wanted to continue with work on electromagnetic induction, which we started. Oh, now we're going to another computer. You can't even do the PDF on that? Wow. Okay, we'll wing it. Now, the point here, there are several interesting and subtle points. It's actually a remarkable phenomenon that Faraday first discovered, and that is that you can make effectively a battery, something which will drive current through a resistor, by varying the magnetic field through a loop. So if you have such a loop, something like that, and you just vary the magnetic field through it, you will drive current around the loop. If you pull the magnet out, you'll reverse the direction of the current. And he studied all these things, the directions and all this kind of thing, and he came up with a law, which we call Faraday's law. Perhaps turn this off. By the way, this is just one of many things that Faraday did. I'd like to talk more about this man and his life, but not right today because we have to move on. An incredible guy. He never even went to college. He was as a kid, 14 years old, he was apprenticed as a bookbinder. In those days, the bookbinder meant you actually bound the pages together. And being a smart kid, he not only bound them together, he actually read them, that was not part of the job description, I'm sure. And he got interested in science. And in those days, they had public scientific lectures, sort of like what we're having today, actually. I don't know if you noticed, There's a professor from... Andre Lindy is coming, yes. This is the honored lecture, Oppenheimer lecture, at the I House at 5:30. Public lecture. Actually, it's often very well attended. 500-600 people show up to those lectures. So go early if you want to go. And those years they had that too. And one of the great scientists of the time was giving a series of lectures. Faraday went with a notebook and he copied everything down. And then he neatened it up, bound it, because you know how to bind books. And he presented it to the professor and said, this is my copies of your notes, the notes of your lecture. And the professor, and by the way, could you give me a job? And the professor said, well, I don't need anybody right now. So as luck would have it, a few months later, the professor had a fight with his assistant and fired him. And he remembered this kid with the book and looked him up and hired him. And before you knew it, the kid knew more than the professor. Because the professor said, look, just follow around behind me, you take good notes. Whatever I say, write it down, sort of thing, and compile my notes. Very amazing story. I can't stop. Well, when the professor went to visit other scientists on the continent, this was, of course, in England, he took Faraday with him, but his wife objected to Faraday eating at the same table as they. So Faraday would eat with the kitchen help, and the professor and his wife would dine with the scientists of the time. Things like that was that class difference. But Faraday started getting ideas and trying things, and before you knew it, he was coming up with great things. And pretty soon they gave him his own lab, and before you know it, he was doing incredible things. You've probably come across electrolysis. There's a Faraday is a unit of electrolytic quantity. The capacitor is called a farad after him. He discovered things like if you reflect light off a magnetic material, you can bend its plane of polarization. We can talk about that. That's Faraday rotation. And this is the greatest of them all right here, because this is the one that generates the electricity that we all use. And the point is that the Faraday law, this Faraday law, the one of many, is that if you integrate along the line here of the electric field, along this line, let me get little s, is equal to minus the rate of change of the magnetic flux with time. If you go around the loop and you trap flux in it, the changing flux, changing magnetic flux. And the magnetic flux, we know what electric field is, but magnetic flux is just a similar thing to electric flux. These are like the number of lines, and this is lines per area, and times the area. So this is a kind of like the number of lines of magnetic field. So if you're changing the number of lines of magnetic field through the loop, you will get a voltage around here. And that, of course, is we've seen this before. This is a way of defining the potential. So this actually is what we call the electromotive force. Now, we're going to have to get into a little more detail what we mean by electromotive force. Kind of sloughed it off before. Before, we had a very simple story. Oh, he seems to have something going here. We used to have a battery, say, and a resistor. And we said that the battery somehow was able to, it had an electromotive force. And that meant that it could push current out through the resistor, and there was a voltage drop across the resistor given by I times R. The energy that the charge gets in the battery is dissipated in the resistor. Now, things I want to point out now that we sort of sloughed over before is that this is an interesting thing, because the charge is going around the circuit. In fact, it's still going through the battery. But look what the charge is doing when it goes through the battery. The charge is going from minus to plus Over here, it's going from plus to minus. Usually you think that, things go from high potential to low potential, which means to say the electric field is this way. Here, the electric field, if you look at it just coldly, the electric field inside the battery is going this way, and the charges are going against the electric field. That's funny. It's a strange thing. And the reason it can do that is there's something in here which is overcoming the electric field inside the battery. In the case of a battery, it's the chemicals inside. We had another example like that I would remind you of it, and that is the Van de Graaff generator. Remember, we had this gadget that looked like this, and there was a pulley being driven like this, and we made some friction over here to put charge, let's say plus charge, on the belt. And the charges were carried up the belt, and then we had a little brush over here on the inside and because of Gauss's law, there's no charge on the inside. So charges on the belt, seeing no charge over here, and there's lots of charges over here that they don't like, the similar charges, they jump off, they go to the inside of the can here, and they don't stay there either. Then they go to the outside, because by Gauss's law, there can be no charge inside. We went over things like this. You may remember all this. Okay, so that all we said. But there's a very interesting thing going on here. The dome is getting more and more plus charge. The charges run all over the outside of the dome. And so the dome, and we keep delivering charge. They keep getting off, not knowing what's awaiting them. They're going to have to get to the outside, and there are even more plus charges waiting for them. So we kind of trick them into getting off the belt, actually, right? So they get off the belt, but they go to the outside. But this whole dome is building up. So we're building up kind of a potential here, because clearly, and we've seen that given the chance, these guys will run away from each other. So there's a big potential difference, a big field being generated by these. In fact, that field is over here too, right? So in other words, those plus charges are going against the field. That's what makes this an EMF. That's what makes this a source of electric field. Because there's a mechanical force lifting these charges into the dome, but before they get inside the dome, they have to run against the electric field. So that's what's going on in the battery too. The charges are being carried up, and they're being carried against the internal electric field by some other property, namely the chemical reaction that prefers for them to go that way. So let me point out that what's characteristic of the EMF is that current tends to go out of the plus side, whereas with a voltage drop like this, the current tends to go into the plus side and out the minus. In a battery or an EMF, the current comes out the plus side and goes in the minus side, because it's pushing the pluses out by some miraculous means that you have to get. Now, Faraday discovered that you could get this miraculous means by putting a varying magnetic flux through a loop. And then he could get the current to go and create an EMF out here. Let's see how that works. What does this mean? Well, this has a couple of very important features. Does anybody need this anymore? Okay. Well, first of all, let me put that down. That you have the EMF. The current is at least trying. There may be a battery or something fighting this other battery and could push things the other way. But at least with an EMF, the current tries to go out the plus side. If that's the only EMF in the circuit, it'll go out the plus side and in the minus side. That's characteristic of EMFs. The other thing that's characteristic of the induction way of doing things, it's the change. Let me make it in big letters. The change in the flux count is the active force, is the active situation. That's what's causing change, not the field itself, but changes that you have. This is one of the tricky things you have to understand, because you see it says deflux dt, change in flux with time. So that's before Faraday. People thought, well, I want to make an electric thing, but I have a field and I'm trying to make current flow in a wire. Nothing happens. But it turns out that you have to move the magnet or move the wire. There has to be relative motion of the two in order for this to work. So let's see what I have in my slides here, if anything that's useful. Okay, well, so here's the basic experiment. We try to set up a bunch of things here. I don't think I really have time to struggle with it, but you did see me do something like have a coil and just plunge a magnet in it, and we got a kick, meaning that some current was flowing in this loop. You must move this. These are the flux lines. If they're changing through the loop, then you'll get flux to come around the loop. Or here, you see, you could have this. Here I had a it's gone crazy. Oh, come on, guy. Wow. I guess the machine is okay. We're way off. Look at all the stuff we have to go through, though. Okay, let's assume. Okay, let's try again. The point is, you don't have to have a permanent magnet. You could even have another electromagnet here. You close the switch, current changes, the flux changes in the first loop, and it'll be picked up by the second loop. And Okay, well, this is what I showed you the last time. So the point is that suppose you had a flux or a magnetic field that went up, you would get some induced voltage in a loop if that were passing through a loop during this interval in time. While the field is constant there, you get nothing. And when you go this, you see the field the current flow would reverse direction and would be slower because the change is slower. Okay, now the other important feature of this is this minus sign. The minus sign signifies that the electric field that is generated here in such a way as to oppose the change that's producing it. So, for example, let's see. Suppose I try to draw a magnetic field coming out of the board, sort of like this, okay? This is coming through the loop. I have a loop, and the magnetic field is going up this way. Now that in itself is not interesting. What's important is whether it's changing and how it's changing. So for example, Suppose it's increasing. So in other words, I have the loop, and the field, maybe I have some currents here that are creating this field B. If it's increasing, what I'm interested in is delta B. That's the important thing. Delta B through this loop. So if the field is increasing, then delta B is positive. It's upward this way. The rule, Lenz's law, this is what this is called, Lenz's law, says that you will get a field, but the field will be such as to oppose that change. So in this case, let's figure out what will oppose that change. In other words, B is increasing, say, through this loop. The direction of the current and voltage will be by the right-hand rule such that the current will be going this way because the field that it creates, which I'll call delta little b, that's the induced field, will be in the opposite direction of the change that created it. And the current will have to go by the right-hand rule number 1. The current will have to go in such a direction to satisfy that. So in other words, this delta B is going to be downward into the loop because B is increasing this way. Delta B would be against it, right? That's the key step. Now, I've struggled to explain this to people for years, and I got an epiphany today. I know how to give you a rule. We've had 3 right-hand rules. I'll give you now, I don't know if anybody has thought of this before, a left-hand rule. Use a left-hand rule. It's interesting, I think. The left-hand rule is that if you have a delta B, that's through your loop, or delta flux, in some direction. You have to give it a direction. In other words, if you had a field, for example, if the field were increasing and B were going through there, delta B would be adding on to B that was there. That would be a positive one. On the other hand, if B is coming through, but it's decreasing in time, in other words, getting less and less in time, then it's as though you added a delta B this way, right? So if B is going down, then delta B is that way because it's subtracting away. If you can get that idea, then this rule is very nice. So if you have your delta flux, so the left-hand rule is that the current that flows, if you point your thumb in the direction of your left hand rule, you point your thumb in the direction of delta B, and your fingers will curl in the direction of the induced current. The induced current will go that way. That's kind of makes sense because if that's a minus sign and all the other rules are plus, why not switch from right hand to left hand and maybe we capture that minus sign? It works, actually. It's quite nice. So what you have to do is find out what is the direction of the change. You don't think about the B itself, the change. What has been added to the field? And then, or let's do a few examples, maybe. Well, let me see if I have something in my... yeah, let's do something pretty nice. Okay, so that's Lenz's law. And, yeah, so, and that, in fact, is the reason. So here's the full glory of Faraday plus Lenz, the minus sign being Lenz. And here's the electric generator. Now, you all hopefully tried to turn the crank and generate field. The reason you had trouble when the battery, when the generator was connected to a lamp, that when current flows, you have a backward force acting on the coils that's that backward negative force. Oh, and I did have this some years ago. When was this? Oh, 2011 already. They tried to get the students, doing the bicycling in the RSF. They were going to attach it to a generator so they could generate electricity while they're working out and maybe light the building and save some money on electricity or something. So they wrote up this thing. It turned out to be uneconomical for some reason. But that's a good idea. I was thinking that would be a good way to stop obesity. These kids sitting around watching TV, you make them pedal in order to power the TV set. Wouldn't that really solve it? Anyhow, here's an example, a case in point. It's a little unfortunate because this particular diagram, they get the direction of current wrong. But let's do this one. I'll leave the left-hand rule up there. But so here's how we would do it. As I see that picture, there is a loop going like this, turning in a magnetic field, and the north side is to your left, North Pole, and there's a big South Pole. So there's a giant hunk of iron. And as I see it, they have this thing turning this way. Did I do that well enough? So this is going into the blackboard here, and that's going into the blackboard and around like this, right? And it's turning this way. So the flux through the loop, you see the loop is starting that way, and it's turning this way. So the flux is actually increasing through the loop, right? Do we see that? Because the loop is like that, and it's turning, so it's catching more of the flux going across. So if the field is that way, delta B is increasing in that direction. So we use our left-hand rule and say if delta B through the loop, let's see, how do I do that? Delta B is this way, so I put my thumb here. Delta B. And the having a hard time visualizing this. Here's the loop. Delta B is this way. I put my thumb here. So but the current should be going around. Let me be sure. It's not as easy to see as I thought. I would say it's going this way. Let me see. Looking at it edgewise, delta B is this way. And I put my thumb in that direction. So the current will be going up this direction, across, down this side, down here, and out here. So that makes this, because this is an EMF, this would be the plus terminal because current is coming out. So you have an EMF across the terminal this way. Now, I don't know what he says. Oh, he has a current going. Well, maybe he's right. not so clear what those. No, he has the arrows coming out of this one. That's what's wrong with this thing. He has the arrow. It's very hard to see. He has the arrow coming out. I have the arrow going this way, out of this one at this point. The loop is turning this way. Do you see this point? That if you have the delta B, I don't care what B is. Delta B is that way, and the proof is that if I take the current this way and I use my right-hand rule to find out what is the field in this loop, it's coming out of this side of the loop, so it is fighting the change. This is hard, huh? Yeah. I tried to make it simpler with the left-hand rule. Maybe, I think if we work on it, we can get it. See, the classic way of doing it is you say I have a change in B, and it produces. You have to get, if the change in B is that way, then the change in your induced B has to be the other way. It has to oppose. And the way to get that is to use, you could use the right-hand rule, say that the current must flow around that way. You know, if the delta B was coming in this direction, then your induced B has to oppose it, and therefore it has to be this way, and to get a magnetic field in that direction, you need a current going in this direction by the right-hand rule for currents. So maybe I didn't, maybe that is that any, not help. Sorry. Oh, dear. Well, it gets to be, you know, to go through it the long-winded way is tedious. But I think that what you have to figure out, see, you start out with a field that's imposed on the loop from outside. So there is the field that is imposed from the outside, and it's changing, plus it's delta B. What's going to happen is you're going to induce a current in this loop, which will have create its own delta B. This delta B is going to be in opposite direction to that delta B. That's what I'm trying to tell you. Can you get that? Suppose this is a loop like that, coming out of the blackboard. There's a B here, and let's say a delta B in that direction. The current that's induced in this has to produce a B opposite to that change. This delta B here is opposite in sense. That is, opposite direction, if you will, to this to the change in the field you're putting on. Does that make sense? The reason it does that, because otherwise, if this were in the same sense, it would just build itself up. If this were in the same sense, B would get bigger, and because it's bigger, another little field is generated, which would add to the first one, and it would just get bigger and bigger, so you get something for nothing. The field would just get bigger and bigger. The fact is that this field opposes you, and so if delta B is positive, if delta B is that way, in a case like this, the current must be this way in order that this little delta B is opposed to the current that produced it. And what this means is that you will find that it will oppose the motion that's creating it. That is to say, well, another possible example. Maybe this one here. can be a little bit hairy, I have to tell you. And the meaning of the EMF and all that is it's a little confusing. But if you think about it long and hard, you can sort of get it. Here's another possible example. Suppose you had a circuit like this. And I take a rod and I drag it. This is a conducting thing, and this is a conducting slider sliding on top of these rails. Now, and I put the whole thing in a magnetic field. Let's say that, magnetic fields, say, going into the blackboard. Uniform through the whole thing. I won't draw them in here because I want to write other stuff in there. But it's all over. Now, if I pull that here, what you can say is that, let's look at the flux in this area here. There's a certain field, B, but there's also an area here. And the area is changing because this thing is moving. So you have in this region here, let's call it, say, 1, you have a deflux dt, which is something like the uniform field. The area is maybe the length of this thing times, well, the change would be the velocity times the length. Because there's certain centimeters per second going this way and times the length here. So a certain area is being swept out here. So the flux being B times the change in area will be a change in flux. Okay, so now let me try to use the left-hand rule, with your permission. So the flux through here is increasing. So that says that it's increasing actually in the down direction. So delta B in here is down because I'm getting more flux in that area. Okay? Or delta flux, actually it should be delta flux. The B is constant, so it's a flux. Is down. And what I'm going to say is that the current is such by the left-hand rule. It's given by the left-hand rule. So that delta B is that way. I would say then the current that runs around this loop by the left-hand rule must run in this direction. So this is the induced current. Okay? So the current is going to run in this direction around that loop. Now let's see if it does the right things. Namely, it wants to oppose the increase in here. And does it? Well, yes. Because, let's see. No, now I have to use my right-hand rule. It's the right-hand to figure out what field this induced current is creating. So I use the right-hand rule to find this delta B. Now, the right-hand rule says that if the current is going this way, the flux caused by this current is in this direction. So, indeed, although the field was increasing in that direction, this induced field, here's my delta B, is caused by this induced current. This is the induced field, caused by this induced current. This is B induced, does the right thing, namely it opposes the change. This is flux is getting larger. This induced current makes it less. Now, how about this side? Oh, and the other thing that's interesting, the fact that I'm pulling this, it wants to resist me. So, for example, what is the force that I have to apply? See, here I have the field is actually going down. The current is this way. The force of the field on this current is given by to find the force on the induced current. The induced current is going this way. The magnetic field here, now I'm dealing with the field, is going into the board. So the force of the magnetic field on this induced current is given by V cross B, or I cross L into B, IL into B. That force is this way. So that means that for me to pull this way, the field itself is opposing me and resisting my pulling it. The field is applying a force back to me. And that's why when you turned the crank, you felt a force opposing you, because you were actually moving wires in a magnetic field, creating currents. Those currents that you created interacted with the field that was there, opposing you. That's Lenz's law in action. So you see, I did use the left-hand rule here, and it's there are lots of other ways of doing it. This is an interesting case. Well, let me point out that what you need to do in any and all cases is change the flux through a loop, and thereby generating a current. That's the trick. Now, in the electric generator, what you're doing is you're changing the angle of the loop with respect to a fixed field. The field is going this way, and your loop is changing its angle, so the amount of flux passing through the loop is changing. That's what you're doing in this case. It's an angle change. There are other ways of doing it. This is the typical electric generator. You're changing the angle with respect to the field, and you change the amount of lines passing through the loop as the loop turns. And you can calculate how much voltage you will get. I make this distinction here. There's two different kinds of things that use a similar kind of apparatus, namely a loop in a magnet. In a motor, you put current into the loop, electricity in, and the force of that will turn the coil in the magnetic field. Or you take the same loop, put in a magnetic field, turn the loop by hand, you generate electricity. So in the one case, you put electricity in, you get motion out. You get nothing for free. If you want to get motion out, you put in electricity. The magnetic forces will act and turn the loop, give you a motor. Or you can turn that same apparatus, a loop and a magnet, you turn the loop with your force, and you generate electricity. Right? So these things look alike, and they can get a little bit confused, confounded with each other. We did this little thing ourselves, and that force that you felt resisting you we could call that the Lenz force. Now, here's another case in point where this is the explanation of nuclear magnetic resonance. Do I have 5 minutes to? Yeah, just about. Well, okay. I don't know if you use, you've done magnetic resonance in chemistry, perhaps? A lot? Some? Yeah. Well, I don't know if you, there are different ways of understanding that. But the way that I have here uses, in fact, the idea that you have a loop and you just make a magnet pass by it. And every time the magnet passes by, it sends a little flux through the loop and generates a little current around the loop. Right? Because we said d phi dt is what happens. So In fact, Felix Bloch was a professor at Stanford. In his Nobel Prize lecture, talks about this. He says, he speaks of the nucleus. The nucleus of proton has a magnetic moment. It's a nuclear magnetic moment. You do nuclear magnetic resonance. It's the nucleus itself. The proton is a little bar magnet, which he refers to here as a compass. And he says, the rotation of our compass needle is accompanied by that of a magnetic field. This is his Nobel Prize lecture, by the way. He's talking to the smartest guys in the world. We understand it perfectly now. This bar magnet is compass needle's magnetic field, which possesses an alternating component perpendicular to the axis of rotation. It's rotating about this axis, but it's going perpendicular, and hence there's an electromotive force induced in a suitably wound coil of wire wrapped around the sample. So what this is, what he does, he puts a coil here, a pickup coil. Do you use this kind of thing, a pickup coil? I don't know what kind of NMR you use. But it is a proton, and it's a spinning top. And you'll see when it spins, way back there you may not see it, but the axis is going like wobbling. Let me see if I can get a bigger angle. Yeah, there it is. See how the axis is wobbling? Now, if I'm a coil here, every time whoop it goes by, whoop it goes by, whoop it goes by, it generates a little bit of a magnetic field because the flux coming out of this magnet is varying. When it's over here, it's one thing, but when it comes by, it generates a little flux, and this pickup coil picks up the fact that you have a precessing magnetic nuclear moment. So, in fact, what they have in the Bloch method, he has two coils. One, he has a coil over here where he sends in radio frequency energy because normally the thing is spinning vertically. But if you put in a magnetic field this way, you can get it to tip a little bit. And once it tips, here we go. Too smooth. Once you get it to tip, then it starts generating field. So you got to prod it to tip with a field this way, and then as it precesses, it generates a field in this coil, and you know you hit it right. To make it tip, you put in a field at the right tipping frequency. Let's see, it's going to start, now it's slowing down. You see, then you would generate quite a bit of flux in this coil. And that's won him a Nobel Prize. And he analyzed it exactly this way. Namely, I have a magnetic moment that's going to be tipped over, and it's going to turn in a magnetic field and generate a sideways thing. And so he went to experimentalists, can you build me some coils, one this way and one that way, one to make it tip, one to pickup coil. On the other side, they tinker, they got it. So this is a nuclear induction. It's called nuclear induction, which was the name of his paper in 1946. So here is a picture of that. It's just called precession of the magnetic moment. And as it happened, at almost the same time on the other coast, Harvard people looked at the same problem, but they looked at it quantum mechanically, much harder way to look at it. Like you put a magnetic moment in a magnetic field, and you have either upstate or downstate. Is that how maybe you learned in MR? You have these energy levels, and you put energy in. I don't know. Did you? Not that way either. You just do it. Don't ask how it works. Well, you can look at it as quantum mechanically, namely energy levels, and you pump energy in. So one way of looking at it is that when the top is spinning this way, it's one energy level. When it's spinning that way, it's the other. And you put energy in, and you can make it jump from state to state, and you notice the absorption of energy when you go from state to state. That's the Harvard way. They shared the Nobel Prize. Purcell and his crowd from Harvard and Bloch in 1952, they got the Nobel Prize. So, as I say, this is a very powerful thing, and simple ideas can go very far. Okay, well, think about left-hand rule. Take care.